So now we're going to be looking at non-standard electrode potentials, okay, or specifically we're going to look at electrodes in half cells where we have non-standard concentrations, right? So far we've seen standard electrode potentials where we were using 1 mole per dm cube solutions, right, for our electrolytes. Now we're going to be using concentrations other than 1 mole per decimeter cube, okay? And before we look at how we can calculate them, let's first just look at an example of an equilibrium, right? Here I have the Fe3 plus Fe2 plus half cell, right, or this electrode, right? And here we have a standard electrode potential of positive 0.77 volts, right? This is again from the data. So again over here I'm using 1 mole per dm cube Fe3 plus solution and 1 mole per dm cube Fe2 plus solution, right, for this particular electrode or half cell, and I've determined this value relative to the standard hydrogen electrode. Now the question is, how can we make this electrode potential more positive? In other words, how can we make the forward reaction more feasible, right? One way of doing it would be to increase the concentration of Fe3 plus, right? That would result in the equilibrium shifting to the right. So one thing I can do here is that if I increase the concentration of Fe3 plus, right? If I increase the concentration of Fe3 plus, right, what will happen? My equilibrium will shift to the right, and then obviously the electrode potential will become more positive. Similarly, if I want to shift this equilibrium to the right, the other thing I can do is I can decrease the concentration of Fe2 plus. If I decrease the concentration of Fe2 plus, again the equilibrium will shift to the right. That's Le Chatelier's principle. It will counteract the change, right? The equilibrium will move in a direction to oppose the change that is made to it, right, or to minimize the change that is made to it. So I can make E more positive. By either increasing the concentration of Fe3 plus or by decreasing the concentration of Fe2 plus. In other words, in this particular equilibrium, what I can say is that as long as the concentration of Fe3 plus is greater than the concentration of Fe2 plus for this half cell, right, I can say that my electrode potential E will be more positive, right, than my standard electrode potential. Again, this is the non-standard electrode potential because we're using non-standard concentrations, right? As long as Fe3 plus is greater than Fe2 plus, the electrode potential will be greater than the standard potential, right? On the other hand, of course, if I decrease the concentration of Fe3 plus, the equilibrium will shift to the left. Similarly, if I increase the concentration of Fe2 plus, right, the equilibrium will shift to the left. In both of those cases, when the equilibrium shifts to the left, the E will become less positive, right? So if I decrease the concentration of Fe3 plus, or I increase the concentration of Fe2 plus, I can say that the equilibrium will shift to the left, and E will become less positive. Okay, E will become less positive. So of course, again, we can say that as long as the concentration of Fe2 plus is greater than the concentration of Fe3 plus, right, that would mean that your electrode potential, your non-standard electrode potential, would be lesser than the standard reduction potential. Now here, of course, we're only looking at the effect of concentration on the equilibrium. Okay, we're only looking at the effect of concentration on the equilibrium. Okay, we're not going to be looking at the effect of temperature. So even here, we're assuming that these changes are being made at a temperature of 298 Kelvin. So now we're going to look at how we can calculate the non-standard electrode potentials. Okay, in order to do that, we use an equation known as the Nernst equation. Okay, we use an equation known as the Nernst equation. So now what is the Nernst equation? Okay, this is an equation that you do have to remember. Okay, in some questions it may be given to you, in others it will not be given to you. Okay, so you have to remember this equation. The Nernst equation is E, okay, is equal to, okay, the standard reduction potential E naught plus 0.059 over Z times log of the oxidized species divided by the reduced species. Okay. Now again, this equation may be given to you in some questions, in others it may not be given to you. Okay, so you have to remember this equation. The Nernst equation is used to calculate non-standard. It is used to calculate non-standard electrode potentials. Okay, non-standard electrode potentials. Okay, so here E refers to our new electrode potential. Okay, E refers to our new electrode potential. Right, if we change the concentration, E naught refers to the standard electrode potential or the standard reduction potential. Right, that is using 1 mole per dm cube solutions. Right, Z refers to the number of electrons. Okay, number of electrons in the equilibrium, in the redox equilibrium. Right, that's when we have to look at the balanced redox equilibrium with the simplest whole number ratios. Okay, the number of electrons, that is the coefficient of the electrons in the equilibrium. Okay, the oxidized species. Okay, when I say oxidized species, I don't mean the species undergoing oxidation. I mean the species formed with the higher oxidation number. So it's the oxidized form of the species, right? So oxidized species is the species with the higher, okay, or the greater oxidation number. Okay, the species with the higher oxidation number, right? And then the reduced species is the species with the lower oxidation number. Okay, reduced species, that is the species in the reduced form, right? The species formed when the electron is gained, right? So reduced species, that is the species with the lower oxidation number. Now let's do a question where the question says calculate, okay, calculate the electrode potential, okay, for an Fe3 plus slash Fe2 plus half cell, okay, half cell, where the concentration of Fe3 plus is equal to 0.5 mole per decimeter cube, 0.5 moles per decimeter cube, and the concentration of Fe2 plus is equal to 0.1 moles per decimeter cube. Now here, right, we have to use the Nernst equation to calculate the electrode potential. Right, we have the standard potential value here, which is positive 0.77 volts. Right, this value is for when we use 1 mole per decimeter cube solutions of Fe3 plus and Fe2 plus ions. So before we even get into the calculation, we should be able to predict that the new electrode potential that we calculate will be more positive. Okay, because here we can clearly see that we have a much higher concentration of Fe3 plus compared to Fe2 plus ions, right? Which means that this equilibrium is further to the right than the standard equilibrium. In the standard equilibrium, the concentrations are equal. Here, the concentration of Fe3 plus is greater, so this equilibrium is further to the right. We would expect the value of the electrode potential to be more positive, right? Now let's calculate it, right? We can see that the equation is E is equal to E naught, which is our standard reduction potential, right? That's 0.77, positive 0.77, plus 0.059 divided by Z. That's just the number of electrons in the equilibrium. That is going to be the stoichiometric coefficient, right, for the electrons. That's just one electron in this equilibrium, right? Again, there's one electron being exchanged, right, or one electron being gained by Fe3 plus to form Fe2 plus. So Z is just 1, right, times the log of the concentration of the oxidized species, that is the species with the higher oxidation number, that would be Fe3 plus, so that would be 0.5, divided by the concentration of the species with the lower oxidation number, that's the reduced form of the species, right, that would be the concentration of Fe2 plus, right. So then what does the value of E come out to? So over here the value of E comes out to positive 0.81 volts, right. So that's your answer. So now let's take a look at the equilibrium for zinc, right. Now here we have the equilibrium for zinc, that is Zn2 plus, right, Zn2 plus 2 electrons, the zinc metal, right, and the standard reduction potential for this electrode or for this half cell is negative 0.76 volts, right, negative 0.76 volts. Now over here I can say that if I increase the concentration of Zn2 plus, right, my equilibrium will shift to the right, right, my equilibrium will shift to the right, and the value for the electrode potential will become less negative, right. If I increase the concentration of Zn2 plus, the equilibrium shifts to the right, and we can say that, right, the E becomes more or becomes less negative, right, or more positive or less negative in this case. Similarly, if I do the opposite, if I decrease the concentration of Zn2 plus, right, if I decrease the concentration of Zn2 plus, then what would happen? The equilibrium will shift to the left and the E will become more negative, right, the E will become more negative. So if I decrease the concentration of Zn2 plus, decrease the concentration of Zn2 plus, right, it means that the equilibrium shifts to the left, right, and the E will become more negative, Now of course over here, right, this value of negative 0.76 volts is for 1 mole per dm cube Zn2 plus. So any concentration of zinc ions greater than 1 mole per dm cube, right, the value will be less negative. It could be 0.75, 0.74, 0.73 as you increase the concentration above 1 mole per dm cube, right? And if it's below 1 mole per dm cube, it will be more negative. So now the question is what is the electrode potential? Okay, what is the electrode potential, that is E, for a Zn2 plus Zn half cell where the concentration of Zn2 plus is equal to 0.3 moles per decimeter cube. And again here we can use the Nernst equation, right? We can use the Nernst equation. Now over here, right, first of all we know that the concentration of zinc here is lower or lesser than 1 mole per decimeter cube. So we expect this equilibrium to shift to the left, right? This equilibrium will be further to the left than the standard equilibrium, and therefore the value for E would be more negative, right? And we can use the Nernst equation. We know that E is equal to E naught, that's negative 0.76, that's the standard potential, plus 0.059 divided by Z. Z here is 2, right, because we have 2 electrons being exchanged, right? 2 electrons are gained by Zn2 plus to form zinc. We have 0.059 divided by 2 times log of the concentration of the oxidized species, that's the species with the higher oxidation number, that would be the concentration of Zn2 plus, that's 0.3, divided by the concentration of the reduced species. Now obviously the reduced species or the lower oxidation number, the species with the lower oxidation number is zinc. It's a solid, it's a metal, right? We just take it as unitary concentration. It doesn't show up in the expression. Okay, just taken as a concentration of 1. Okay, so this is our expression. and we get the value for E as negative 0.775 volt. Okay, so that's our answer.